presentation, and Alex was quite interested in this work that was not published yet, not on arXiv. As you can see why, because there are a lot of people on the paper, and you know that usually the time spent on this paper is proportional to how many people involved. But anyway, we close to finish it, and we wanted to have it as a birthday present for Alex, but failed. But however, let me just present the content and some elements of the proof that Alex is very interested in. Also, we just start with each term. Geodesic in this context will always be hyperbolic geodesic in a simply connected domain with which is not the sphere or the complex plane. So it just means that so there's always a hyperbolic metric on such a simply connected domain, the geodesic connecting two boundary points. For complex analysis, it just means the image. If I map conformally this domain D to the upper half plane, sending this point to 0, this point to the other point to infinity, this is the imaginary axis. For probalist, which I am, it just means this is the collection of points where if you start running a two-dimensional Brownian motion, these are the points you will have equal chance to first hit the left-hand side, right-hand side. And Brownian motion, two-dimensional Brownian motion is conformally invariant, so you can also talk about Brownian motion here. And this curve will be the points for which, if I start the Brownian motion, it will have a probability 1/2 to hit first here, then probability 1/2, then hit here. Geodesic property. You have already heard in Evelina's talk, and if you look around on the poster, our poster was explaining what this geodesic property in one particular case. So that actually arises from the study of multi-chordal SLE that Evelina has been explaining. Let me just remind you. So if you have a multi-chord, so meaning like n disjoint curves connecting two pairs of two end points on the boundary, like they're paired to n pairs. And the geodesic property means for each of this curve, like say this curve, it has to be the hyperbolic geodesic in the union of the two faces adjacent to it. And this is appearing as the multi-chordal SLE0, but you can take this as just definition of a multi-chordal SLE0. And this relates to some work of Alex and Gabriela, that in fact, in order to classify all the possible geodesic multi-chord, we relate this to rational functions. I mean, just recall how does that work. So now if I have, just draw a picture here. If I have this right here, I can first consider for this domain, I first map it to the upper half plane. I take arbitrary map to the upper half plane. And now the green curve is maybe somewhere here. And now if I consider a new map, which is taking the union of the two faces, so it will be the boundary of this face is be here, right? This union of the two faces to the domain where I remove the two. I take the union of the upper half plane, lower half plane, and the green line. It's a simply connected domain. This yellow area is also a simply connected domain. I map it to the union of this and the green line. So this is a map between a simply connected domain to a simply connected domain. and also sending the 2 points, the same 2 points. The geodesic property would tell me that this green curve has to be mapped to this line because this is the hyperbolic geodesic. It's a point where if I start the Brownian motion, it will have the property will have to hit it up or down. So in other words, this new map extends my previous conformal map. So everything I use is the geodesic property. Right? Whenever I have a map from the upper half plane, this side to upper half plane, the geodesic property allows me to extend analytically such that the face outside will be mapped to the lower side. Here now. So this face will be mapped to the lower half plane. We can keep doing this. This will be mapped to upper half plane. This is mapped to lower half plane. And since that if you look at the image of the real line here, the real line is always mapped to the real line. Also, these curves will be mapped to the real line, but especially the real, here this real line will be mapped to a real line as well. The Schwartz reflection allows me to reflect everything down there, such that this place will be mapped to, we have this alternating coloring. This is a branch cover of the sphere. This gives you a rational map. All right, we can think of this as my new graph. My graph will be given by these edges, the reflection of the edges, and the edges which is connecting these critical points. And this is a graph with a this. And more generally, what do I say? What do I call? So a graph, embedded graph, which was with the geodesic property, this will be. I'm not going to write down, but it always means that each edge is embedded such a way it is a geodesic union of the two faces. But there's not always a rational map that is associated to it. Not guaranteed, because here, if you have another graph, even the simplest one, a graph with full vertices and full edges, I can repeat this trick. Every time I have a face, I can map it to the upper half plane, and I can keep extending. The normal guarantees me that if I extend it to outside and come back here, I get the same map. Here it works for the rational function is because we have this symmetry of the graph, and the Schwartz reflection somehow magically make it work. So in a more general setup, it's not always related to a rational map. And let me give you some more example of well, we'll look at Jordan curves with geodesic property. They will be all curves, graphs of degree 2, like looking at this. Examples of geodesic Jordan curves with geodesic property. Well, if you have a circle, it must be a curve with geodesic property because this property will be invariant under conformal automorphism. In particular, you map to the real line. So each curve has to be the hyperbolic geodesic in the complement of the rest. Circle. You can even talk about 2 points, right? You can just in two curve, there's a circle going through 2 points. There are also other curves, like say, if you take I'm going to construct it this way. I take an infinite strip, say passing through 0, and this line is the translation by 2 pi I. my strip. I take the line which is parallel to this boundary, but in the middle, so it passing through pi I. And I look at its image under the exponential map. Right, what it does, so this side it goes to we go to 0 in the image. But this point will be mapped to the same point by this exponential map. So this map is giving you the white curve will be a spiral, logarithmic spiral. And the red curve, I can't draw infinite spiral, but it's infinitely spiraling inside, but comes like this. Topologically, this is also a curve which is going through 0 and infinity. Topologically, it's like a this curve. Right? But it also has the geodesic property, right? Because this red curve, it is a hyperbolic geodesic in the strip. But this is also the image of you can just transform this. This is also the image of this guy. So this white curve is also the hyperbolic geodesic in the complement of the red curve. So actually the spiral would be interesting case, but today we want to rule out this situation to happen. So today, our goal is to understand Jordan curves, P1 Jordan curves. With geodesic property.
They're marked.
With the points marked, yeah. So let's consider this.
Excuse me?
Yeah.
Could you explain some motivation behind that problem? So is it a theory or something?
Yes, so this one will be yeah, well, so first of all, this is like I didn't want to mention SLE too much because it's purely like stated in the complex analysis way. But one of the motivation is actually for Jordan curve case is especially it will be related to SLE loop measure. But I actually won't be talking too much about SLE loop measure. Like the curve which will have this geodesic property, there will be like SLE loop condition to passing through these points and letting kappa goes to 0. But I mean, if you need to talk about this, you don't need to mention SLE. I would say a little bit more. So first of all, we say if I give you these points, let's say assume that this is 1, 0, you can always normalize 3.01 infinity, and I give you like Z1, Z2, Zn minus 3. Does there exist? Existence? One thing one actually can try to do is that, I can start with an arbitrary curve. I want the geodesic property. I would just try to give a algorithm where every time when I see this observe these 4 arcs, I would just replace this curve by the hyperbolic geodesic. And then I can do this. I replace by hyperbolic geodesic. But once I replace this by hyperbolic geodesic, this one is not anymore the hyperbolic geodesic. So one need to argue if I do kind of this algorithm, whether it terminates. And
hyperbolic geodesic in the complement of the other.
It's always in the complement of the other as the graph. So you always look at the domain, which is the union of the 2 faces and also the edge itself. So in order for it to converge, we need some compactness. And in fact, there's a functional which is decreasing when you do this algorithm. This is also actually in our case how we show that this geodesic curve exists. We actually introduce some Lerner potential, and for which these curves actually minimizes the Lerner potential. Let me here just define it. So for curve gamma, the Lerner energy for gamma is defined as 1/pi this is the Euclidean parameter 1/pi. All right, I will tell you what these are. 4 times log f prime 0 divided by g prime of infinity. Okay, f and g, the unit disk. This is the outer disk. F is conformal map here, and the G is a conformal map. F is going from the unit disk to the inside one side of the curve, and G is the map from outside of the disk to outside of the curve. And we need to normalize it so that it seems to be finite. I just asked G infinity to be mapped to G infinity. Okay, this definition, some remarks. So in fact, the Lerner energy originally has a different definition where I'm not going to talk about this, but it's introduced in the golden curve case by Stefan and myself. The right-hand side, it has another name called the universal Liouville action. Is introduced by Tatajong and Thiel. These two definitions. So this equality, this is a result by myself in 2019. So now you can just consider this as a definition. Property, this functional has attracted a lot of attention because let's give you some property of it. So first of all, this is a PSL is a negative invariant, PSL to C invariant. You may try to prove it, but it's not so obvious actually. This quantity is always non-negative. Also not so obvious from this expression, because actually this term is negative. The other two terms are positive. The Lerner energy is finite if and only if gamma is the Peterson. Which is also this L2 universal Teichmann space. We heard about. And the Shah has a paper about this, like basic, if you equivalent description of this. And my motivation is actually coming from the relation to SLE that maybe answer the question before. Very roughly speaking, Lerner energy is the action of the SLE. So SLE kappa, absolute 1 kappa is between 0 and 4. Loop measure, its density is proportional to exponential a central charge of kappa over 24. times the learning energy. Where central charge is a explicit function of kappa. So in Evelina's talk, you heard the results about kappa goes to 0, but actually there's also a version for fixed kappa without letting kappa goes to 0. So this is a recent work by so Kappa Nini, who is a postdoc, I think he's moving to Australia soon, in San Diego, and myself. And also, finally, for right, and this is in terms of the tail, why they look at this functional is because this quantity is a Taylor potential. On this L2 attachment space. So, fact, are there questions actually about this?
So PL special to C invariant, this is precomposing, right?
Post-composing. Post-composing, yeah.
Post-com-
Yeah, pre-composing will be a PSL2R. Pre-composing, that's also invariant. So
Okay,
this
PSL.
definition doesn't depend on which FG you take. Okay, so how this functional is helpful to our question. And actually, you will see that this quantity is really essential to it's not just a tool. It's going to be really essential to discuss this family of Jordan curves with piecewise geodesic property. So in fact, if I give you this, if I minimize the learner energy. So first of all, if I replace the curve by the geodesic, the energy would decrease when we replace each piece by geodesics. And also for those Jordan curves, gamma for which the learning energy is less than a number, big N number M. They are inside the family of K, which K is the number depending on M, quasi-circles. I remind you, K quasi-circle meaning these are the image of the round circle under a K quasi-conformal map. So here this is a bound. So if I can bound the energy from above, then the quasi-conformal constant will also be bounded. And this will give us the compactness assumption. So this would imply this algorithm will terminate.
Terminate or converge?
A convergence, yeah. Okay, this is for the existence. In fact, we can do a bit better. For existence, we can even assign the homotopy class of the curve. So it's not only the location of the points, but also a homotopy. Okay. Like when you have more than 4 points, there is already infinitely many homotopy class of vectors, like homotopy real z1 zn minus 3 0 1. Right, so relative homotopy just means that two curves are homotopic if you can deform them without leaving these points. Like this curve and this curve, they're homotopic. But this white curve is not homotopic to, let's see, you can still visit the point in the right order. First one, this one. This is a different homotopy class than this one. And even if I fix your homotopy class, my algorithm, it still works, right? I can still replace each curve by the hyperbolic geodesic. It wouldn't change the homotopy class. So this actually, we get that existence of geodesic curve in each homotopy class. I will denote my homotopy class by this. So Z1, Zn minus 3, 0, 1, infinity. And also, I will just write this to say this is a homotopy class. So the homotopy can also keep track of the location of the points. Now the question is uniqueness. And assuming C1. We already see if we don't assume C1, even for the 2-point case where you have 0 infinity, there's a family of curves. So we will just take the C1 case. So the uniqueness within each homotopy class. Alex was very interested in seeing the proof of this, so I'm going to give you the elements of it.
Is it clear that the one that you get from this process is C1?
Yeah, actually, it's a good question. In fact, if it's not C1, yeah, okay, let me comment on this. So, this is, yeah, there's actually like the dichotomy. Either there is a spiral that's not C1, or one there is it's C1, then the curve is actually going to be C11. There will be like analytic curves. This curve will be analytic, and their derivative are matching. So they're actually a bit better than just C1. And in this case, then there's a condition about the Loebner energy to be finite. There is sufficient condition for Loebner energy to be finite. It's 1.5. Better. So this is already much better than C1.5.
Okay, so as long as you start with one which is kind of C1, then you'll always stay that way, is that right?
Right. Yeah.
If your potential goes down.
Yeah. But actually, this process the convergence will not be in C1 because you can start with a curve with a certain angle. So in the limit, there's actually a unique limit. The angle is somehow prescribed by that unique limit. So,
Mm.
so in the end, although it's C1 all the time, but it's
Yeah.
kind of slowly turning it. Right. So, the element of proof. You need to guess. So yeah, the answer is yes. Assume I will just draw it in 4-point case. Assume I have two curves with the geodesic property. Assume two curves that are homotopic to each other. And with the geodesic property. We want to measure how far they're from each other. And in the end, we want to show this their distance is actually 0. And it proves the uniqueness. Okay, so how can we measure it? I'm going to define a function on the red curve and take the white curve as my reference curve. And I want to see each of the red curve, how far it is from it, from the white curve. So first I define a function for each of the piece, say on this piece, this piece. It's not, I want to know whether it's how far it's from this one. Right, for this one, how can I going to measure it? Well, this is the points from which I start the Brownian motion. It will have probability 1/2 to hit the left hand side, and probably 1/2 to hit the right hand side. Or if you want, you can just consider the harmonic extension. This is I put 1, so plus 1, 1, 1. So on the inside of this curve. And put -1, -1, -1, -1, -1, -1, -1, -1, -1, -1, -1. So now I look at the function which has a discontinuity across the green curve, and this equals to 1 on this side, but -1 outside. And then look at this harmonic extension. The white curve has to be a geodesic, so I know that the white curve, this will be equal to 0. Right, the harmonic extension. And now for this red curve, I look at the function, it will give you some value. I define my function rho. So let me call this harmonic function. This white curve called gamma 1. So the harmonic function, I call it the h1. And I will take rho to be absolute value of h1 on my curve. This is gamma tilde 1. Gamma tilde 1. The rho restricted to gamma tilde 1. Right? Okay, now you say it doesn't mean that my curve has to, my red curve doesn't have to avoid the green curve. But if it doesn't, so now this value has to be in between 0 and 1. But if it actually hits your green curve, we can actually like harmonic extend it, okay, so that this rho will take value larger than 1. So one rigorous way to do it, you can take the universal cover of the punctured sphere and look at how you can define this harmonic function on the universal cover. Let's just stay with the schematic picture here. So this one is going to give me the value, tell me how my gamma 1 is away from, gamma tilde 1 is away from gamma 1. I will define rho on other curve in the similar way. I will take rho on gamma k of . for each of the red piece, I will use the corresponding harmonic function to measure how far this red curve is away from the green curve. And once you keep doing this, I define a function on the red curve. And then we extend the definition. Then we harmonically roll to both omega tilde, so that's inside of the curve, and omega tilde star, omega tilde and omega tilde star. So now I get the real positive function on the whole sphere, which is a harmonic in these two sides. So what we prove is that rho is bounded. This is actually not hard to see that as long as this rho is bounded on the whole red curve, it's going to be bounded, its harmonic extension. But more importantly is that rho is subharmonic. It's harmonic inside, so it's only what you need to check is on the curve. Okay, what's subharmonic? It just means that it's below the harmonic functions. So intuitively, what this means is that
Where it's subharmonic?
sorry,
In which domain it's subharmonic?
on the whole sphere. Yeah. Anyways, harmonic outside.
So did you say the rho has an interpretation in terms of Brownian motion? Or did I miss here?
Yeah, right. It kind of there's a Brownian motion lurking behind. Like for this rho, it will be so this value of it will be like the probability of so it's 0. This means the probability difference of the probability from 11. Maybe I had to divide by 2 or something like. This is so basically this is the probability of Brownian motion starting from here to hit first the left versus the right hand side. Yeah,
Okay.
after a factor. Yeah, okay. So what this subharmonic means is that if it is subharmonic at this point, it just means it will be smaller than the harmonic average of the value elsewhere. So it just means that since my red curve has a geodesic property, if I start the Brownian motion from here and stop at the first time it hits my red curve again, and I read what is my deviation at the other points. Subharmonic means that the average deviation will be larger than the actual deviation at this point. Okay, so otherwise you can think of assume that all my other curves they deviate by a certain amount, like C. Then the deviation on this curve will be less than C. This is what the subharmonicity is telling you. But once so this definitely is not a simple, easy proof, but we need to use like really heavily on choosing cleverly how to use this geodesic property. But intuitively just says that if my curve away is deviate by a certain amount, here the deviation should be less than that amount. And once we have that, like for the bounded subharmonic function on the sphere, a puncture sphere, this will actually imply that rho is constant. Let's say equal to C, which is positive or equal to 0. And right here. Now the final step is to show that this constant has to be 0. And this is a so what we roughly speaking, what we try to do is that if you have endpoints, so if C is strictly positive, so this is my first curve, this is my reference curve. This would imply that the red curve will be on one side of the curve, and basically we show that if the red curve is on one side of the curve, the other side has to be all the inside of the curve. So this is it's not like very transparent from here, but this is roughly what we're trying to do to show that if it's getting positive, then all curves have to be on different sides with each other. And this is only possible when n equals to 2. So, which actually is true that for if you give 2 points, there are like infinitely many sphere circle you can go through it. Right, this is the circle going through it. And so when n is larger or equal to 3, there's a uniqueness to that Z curve. Okay, we actually have used the C1 property when we get this row. Row is well defined and row is bounded. If it has spirals, row won't be well defined. So it's actually. Okay, so I hope Alex will be roughly satisfied about this sketch of fruit. In the remaining 10 minutes, I would like to give you a more geometric interpretation of this result. In terms of the projective structure on the sphere.
Sorry, so when it comes to the uniqueness, so you've used the C1. Are you saying that if you don't have the C1, then for n greater than 2, it's not unique? Or
Yeah, even n equals to 2 is not unique.
but for n equals 2, it's kind of not unique already, right?
Yeah, right. For others, you can also construct a spiral case very easily. Okay, so one interesting thing that is associated to this Jordan curve, or erase this. Right, so you have to have a Jordan curve. We can talk about its welding homomorphism. So there's F, G. The welding of gamma is defined as G inverse composed with F restricted to the circle. Right, this is a map from S1. So this is well defined. This is well defined up to PSL2R. Find PSL2R. You can pre-composing, post-composing. So basically, phi would be the same as A composed with phi, where A, B, and PSL2R. The disk automorphism. And we claim that it's easy actually. Lemma. If gamma has geodesic property, gamma has geodesic property if and only if phi is piecewise. Oh, do you see that? Well, F and G you can choose really freely, right? There's a map Here is a conformal map. Here is a conformal map from the complement of this circular arc to the rest of the curve. This is geodesic. This is geodesic, so it's well defined. So if you restrict it to inside F and G, they actually coincide here. So here F and G. Now what is phi here? Then phi at this point there will be just identity. Because F and G they're the same. Right, so because this is well defined up to PSL2R action. So the part of the welding has to be PSL2R. Wait, this is a just need to look at stera and part. And has piecewise geodesic and C1. This will be equivalent. Piecewise geodesic and C1 will be piecewise PSL2R plus C1. But this is the case we are looking at. And okay, once we have this PSL2R, then you can define something really nice. If you look at the Schwarzian of F inverse, right, going from here to here, this will be the Schwarzian of G inverse composed with F composed with F inverse on gamma after removing these points. Okay. Because this is a Möbius. The chain rule of Schwarzian will give you they're actually the same guy. Okay, what do you have now? That this Schwarzian is a holomorphic function inside and outside and coincide along the curve. So this defines a meromorphic function. C hat. But we had to actually, in order to show this, we actually even compute how the Schwarzian this function looks like. I call it phi. And for our theorem, that this phi of Z is a sum of Z minus Zi. So now I runs from 1 to n. We need to interpret a bit when it's infinity. But at other points, it's exactly has a simple pole at each point. And it goes to the whole meromorphic function with a simple pole at infinity. And Ci, this is called the accessory parameter, is equal to the Wertinger derivative over 2 of the Lerner energy here it's a bit different. This is the minimal energy or the energy of the unique geodesic curve going through these points with the okay, so if I have this curve, I want to know what is the C, what is the parameter C here. What I do is that I just perturb slightly this point and look at how the minimal energy changes. And this will give me the number C, which appears in the constant here. And the proof of this thing is really purely computational, and because we understand really well the Lerner energy, how they work. But let me give you a further interpretation of this.
So this is like in Zograf and Takhtajan, yeah?
Exactly. I'm going to relate to that.
Mm-hmm.
That was for the Fuchsian projective structure. So one could have noticed that the fact we are taking all these possible choice of homotopy class is actually in bijection with the Teichmann space of n-marked n-punctured surface. Let me remind you what this means is that, so for Teichmann space, let's say I would take always 3 points here. This is my sphere. This is my reference surface S. For Teichmann space, these are quasi-conformal map of the punctured sphere to some other punctured sphere. Up to the Möbius transformation. So I also assume this is there is a 1, 2, 3, 0, 1, infinity here. So this is my surface X. So the Teichmann space, these are the collection of pairs X of S up to an equivalence relation, where the equivalence relation means that if I take F1, X1, and another pair F2, yeah, they are always normalized, so they're always fixing 0, 1, infinity. The Teichmann space, the equivalence relation says that there exists a conformal map phi. Now they have to respect the marking, so actually phi had to be identity. So X1, F1 is equivalent to X2, F2, if and only if phi is identity. So phi, which is identity, which is going from X1 to X2, and F1 is homotopic. Is topic to F2. Here, there's no curve, but if you want F1 and F2 to be homotopic, you can just say, like, I can just mark a curve on it going here. And here it's going the image going to here, to here. If the surface there will be as a topic to each other will be equivalent to the curve to be also equivalent homotopic to each other. And that's why you have this identity with so now we come back to what the statement we had is that for each point in the Teichmann space, there's a unique homotopy plot. Therefore, there's a unique curve with the geodesic property and C1. And now what did this Schwartzian has to do here? So the Schwartzian, they actually encode a projective structure on the punctured sphere. What do I mean by that? The projective structure, we have the two surface. I remind you, what is conformal map? Conformal map is a homeomorphism which preserves the complex structure. Complex structure means that if you take two charts, you have two complex charts. Complex structure means that this transition map is biholomorphic. This complex structure. And if I ask this transition map to be projective, meaning like a Möbius transformation, then this is called the projective structure, complex projective structure. example, on the puncture sphere, there is a trivial projective structure. So the map, I call it this phi u and b. This is a local charts map. This is u and this is b. A trivial projective structure where phi u will just be identity on u. It's a so this is a projective structure. They're always going inside the sphere. Talk about PSL2C on this. And the trivial projective structure, their charts are just identity. And there are also function projective structure. What you do is that, you know, for each of the surface, there's a covering map phi, which is holomorphic, covering the sphere. And the function projective structure is given the charts phi u is equal to pi inverse restricted to u. It's not well defined. Like see, for the inverse of u, this is a map going to if you take any lift. Any lift, they will only differ by a PSL2R equivalent, which is in particular projective. And in our case, we also have a chart, which is given by our curve, Jordan curve with geodesic property, where phi u will be F inverse or G inverse, depending on which side of it you have. And it also extends across. Right? It also extends across because we can actually have a choice where F and G they're equal. So these are all different projective structure, and the Schwartzian is measuring the differences between them. So the Schwartzian is always like a quadratic differential, which is measuring the differences of two projective structure. And now this will if you measure the trivial one with the function one, you're looking at the Schwartzian of pi inverse. And Alex he was mentioning that in the Taktajan-Zograf theorem, where they proved that the Schwartzian of pi inverse is of the form also the sum, but there's a double pole, so minus 1/2 v minus zi squared, plus there's then a simple pole, it's a different number, v minus zi. And this is actually the classical accessory parameter that the Poincaré Polyakov talking about. In our case, what we get is the Schwartzian of F inverse. They are given by only the simple poles, Ci, C minus Ci. So these Ci's, they're not really related. At least we don't know how they're related. But finally, I mean, just draw a schematic picture what we ended up having. You know, the Eichmann space, let's draw this here. Now the projective structure, they always descend to a complex structure. If I ask my transition map to be projective are always biholomorphic. So it's actually a fiber, and now each point, there's a fiber of the same dimension as the Eichmann space. So what we have is we obtain a section for our coming from the Jordan curve with the geodesic property. And there's a function section They're never the same. Projective structure. And in fact, we even have a very simple way to go from one to other. We can also relate these two sections by grafting. Roughly speaking, what we can do is that if I have this our piecewise geodesic curve, and if I draw the geodesic, okay, let me just draw here. My piecewise geodesic curve. I can draw the hyperbolic geodesic connecting them. These four inside. And geodesic outside. There's a natural identification where you can collapse these annulus, this disk. It's kind of degrafting, you just collapse them, and then now this angle will become zero angle. We can pass from one point to another point for the Fuchsian projective structure. Yeah, so it's actually reminiscent in people doing like attachment theory, where saying that you can induce a homeomorphism of the attachment sphere if you just project out. It's the grafting thing. Okay, let me just stop here.